Here's 11.2. I'm actually going to call it day 1. It doesn't show this up this way on our schedule, but I am actually going to split this up into 2. There's a lot to cover here, and it's going to be easiest in 2 days. We're looking at converting complex numbers to their polar form, which you're going to see is really, really similar to converting any coordinate point to its polar form. But first I want to cover complex numbers in standard form. Okay. We have the real number line, and then vertically we have the imaginary number line, which was born the day we took on trying to answer the question, what is the square root of -1? And real numbers did not yield an answer. Okay, so we think of the real component of a complex number like x, and b is like y. Okay, so if I had 2 minus 3i, I'd add 2 to the right, and down 3. Okay, it would be 2 minus 3i. 0 plus 4i would just be up 4. -1 plus I would be 1 to the left, 1 up. 3 plus 0i, which is better known as the real number of 3. Notice how it sits on the x-axis because its imaginary component is 0. Oops. All right, we're going to take a peek as to how we convert these. Again, I'm not even going to go through the derivation because it's so similar. Again, because we're thinking of the real component like x, that becomes r cosine of theta, and the y is like r sine theta. Now we can, the way this is written, notice it's a little bit redundant in polar form, which it's the same idea of defining the location of that complex number in the complex plane in terms of r and theta as opposed to x and y. Okay? This definition here is a little bit redundant because notice that you see r twice and theta twice. We could take out a factor of r and have cosine theta plus sine theta times I. But then this whole piece right here is a little bit redundant. The theta is there twice. So we could go r, and this is pronounced cis, stands for cosine, imaginary, sine. I'm just writing in how it's pronounced. It has all the information that we need, r, theta, and imaginary. So if you see 2 cis 30, if you wanted to write that out the long way, you could say 2 cosine of 30 plus 2 sine of 30 times I. Okay, that's its meaning. All right, so we go through a very, very typical sequence of events here to get r and theta from essentially x and y. So here's -1 minus 2i okay. In fact, I'll zoom in to get it a little, whoops, to get it a little better. So there it is. I want to convert it to polar form. Okay. What I want you to notice on here, I'll zoom in a bit. It's really not different from the previous conversion that we did. Okay. -1 is like x. -2 is like y. Again, this represents the real number line, and that's the imaginary. Okay. We need r, and we need theta. Okay, we need r and we need theta. notice we have x and y, so as it seems like is always the case, the Pythagorean theorem of x squared plus y squared, that will yield r, okay, just like it typically has. Now to get theta, well, I'm going to finish this off first, and let's see if we get 1 plus 4. So we've got the square root of 5, okay? So that would go right in this diagram. There's r as the square root of 5. And now we have any number of options to get theta, because we have x and y and r. We could use sine, we could use cosine, we can get tangent. Anytime we're looking for a missing angle, we have to think inverse operation. For no particular reason, I think I will go with sine. And do the inverse of -2 over the square root of 5. Okay, now it's really good to make a graph because it's good to think about what quadrant we're in. And right here I can see that I am in quadrant 3. Now when I punch this into my calculator, I got negative 63.4 degrees. Okay, we haven't really talked about why sometimes the calculator gives us some kind of strange answers with the inverse. There's a very good reason for it that has to do with the domain and range of the inverse function, which we have not studied in any detail. Remember, if you want to get a second solution or an alternate solution with sine, you can always do 180 minus the answer you had. So if you want another solution, we could just take 180 and we could subtract negative 63.4 degrees. That gives us 243.4, which is a much better answer as it's right where we expect it to be down in quadrant 3. Okay? So now for the final answer for this complex number. Remember, that's the whole thing I'm doing here, is rewriting this in polar form as opposed to standard form. Remember, it goes r cis theta. I found out here that r is the square root of 5, cis 243.4 degrees. Okay, and that complex number has now been converted over to polar form. Okay, switching over to rectangular form is actually quite a bit easier. What we really have to remember here is just a longhand notation of what this means. Remember that it's cosine, imaginary sine. So this represents 2 cosine of 45 degrees plus 2 sine of 45 degrees times I. Okay. Once you have it to this point, it's a matter of simplifying. Okay, I could go to the unit circle if I needed to. By now you may just know that cosine of 45 is square root 2 over 2. Same with sine. 2's cancel. Real component square root 2. Imaginary component is square root 2i. Okay. One thing you'll want to do, as far as graphing both of these, I could look at that really quick too. Remember, in polar coordinates, I would go to 45 degrees and then a length of 2 units away from the center. And now in standard coordinates, you may find it useful to just go to a decimal approximation. Square root 2 is kind of hard to visualize, but when I convert it, I go 1.4 to the right and 1.4 up. And that is the best way to get that number on the graph. Okay, so when you have those square roots of whole numbers, don't be afraid to look at decimal approximations when you're graphing. Okay, so there's an example of each standard to rectangular. There's one more thing I'm going to show you in day 2, which is how to multiply two complex numbers in polar form. All right.